Now we will now look into bolt group loaded in plane. Now, if you look at the bolt group subjected to in-plane loading, it is your clause has been changed now. So we have the, sorry. That's in the new standard, some of the clause number has been changed. So it is clause 3.9.1, which talks about bolt group subjected to in-plane loading. Now, look at this figure. In this case, you can see that all the bolts are actually subjected to the forces or moment, whatever, that's in this plane. That's why it is called loaded in plane. Now, when you design these particular connections, you have to follow some assumptions. What are the assumptions? The connection plates are considered to be rigid and rotate relative to each other about the bolt group centroid. That means if you think of this is the bolt group centroid, which is the instantaneous center of rotation, that means the connection plates are rigid and they rotate relative to each other about the bolt group centroid. This is a very important assumption. And the design shear force in each bolt shall be assumed to act right angle to the radius. That means you see in this case, if you have nth bolt, then suppose that's the radius, right? Suppose that's the radius. That means if you draw the tangent to that, that means right angle to the radius, that actually will tell you that this will act right angle to that radius, to the, when you draw the radius from the centroid, and shall be taken as proportional to that radius. That means the simple thinking is this. Simple thinking is as you go further from the centroid of the bolt group, that means it will carry more and more force, yeah, isn't it? Because it clearly says that the design shear force for each bolt will be taken as proportional to the radius, and radius means it is the distance of that particular bolt from the bolt group centroid, which is basically the instantaneous center of rotation. Okay, right. Now let's look at the figure and then it will be clearer. So if you are this example, that will be more clearer to you. So if you look at example C2, the bolt group in shear, you can see this one, this is a flange of a column, and then we have the two plates on both sides. You can see there are two plates on both sides as you have shown here, and there's a bracket. So this is a kind of bracket. So basically what has happened is that we have actually a bracket type connection here, okay? So this bracket type connections and the connection and the load is applied here, okay? So what we have said is determine a suitable bolt size for the joint shown below to safely support a vertical load of whatever 400 kilonewton. Bolts are of this grade and the plate is this grade with 8 millimeter thickness. Now, the important thing is to understand what is happening there. Now, if you think of this load is applied here, right? Ultimately, what will happen is this connection, yeah, this connection has to transfer the bolt, transfer the load to the flange of the column, isn't it? So it's a kind of, it's a bracket, yeah? So we also many times, call it corbel type connection. So what happens is if you transfer that load along the center line of the column, what do you get? That means the load you can easily transfer there. And what else will happen? Because we have a load transfer there, there's an eccentricity. So actually, when you transfer the load to the centroid of the connection, we'll have the same axial load or the vertical load. Sorry, not axial, the vertical load, that means 400 kilonewton. And there's a bending moment. So that means essentially you could think of this will be 400 kilonewton, which is fine, which will actually produce the shear force because that will directly, it will act in such a way, it is acting, you can see that all the bolts will be subjected to shear. And then you have a bending moment where the moment is actually given by 400 times 0.3, which is your 120 kilonewton dot meter bending moment. Yeah. Okay. So that's the thought. That means then the connection will be actually carrying 400 kilonewton and the 100 kilonewton meter bending moment. Then because there are two sides, so automatically those load will be half. That means on each side it will be carried the half of this 200 kilonewton and 60 kilonewton meter moment. Okay. And this, edge distance and this pitch of the bolts are provided. Now we have to select or design a suitable bolt size. Okay, so design each side of connection of 200 kilonewton force. We have looked into that. So the direct shear is divided equally among the bolts. This is understood. We have 8 bolts we have shown here. Now you can have any number of bolts. So if you divide the number of bolts by the number of bolts, you get that each bolt will be subjected to 25 kilonewton shear force. Then you are looking at the bolt group. Now, if you look at a bolt group, it is shown here like this. You can see this is the centroid. Now, these plus signs actually represent those bolts or the centroid of these bolts. Yeah. So you can see what it says is that the bolt group rotates about its centroid, and as a result, we are getting a linear variation of bolt loading. That means as we talked about before, furthest is the bolt away from the center of rotation. It will carry more force, isn't it? That means we will then you have to check the bolt which is situated at or located at furthest from the centroid of the rotation, isn't it? That's very important, yeah? Or the center of gravity of the group, isn't it? Yeah. So we are interested in carrying those distances now. Now you have seen that the spacings are already provided. So this is 50 and that is 150 and that is your 300 we know, and this is also 50. So what one could say that if this is the bolt is P1, where the bolt force, the shear force is acting as normal to the radius. See, this is the radius, so normal to the radius. And one could say, as based on the assumption, that P1 will carry a force which is proportional to 158. Now, what is 158? 158 is basically the radius. If you say this is R1, one could actually write this R1 is basically given by 150 square plus 50 square. Yeah. So that's the radius for bolt 1. And then if you look at bolt 2, where you have the proportional to 70.7, this is your bolt 2, which is 50 square plus 50 square, right? So that is so what we are saying is, as per the assumption, that the load will be proportional to the distance, the radial distance. So now if you take the ratio, that means if you divide one with the other, you get this one. That means you are getting P2 is 0.447 equals P1. Now, if you look at this problem here, it is basically a statically what? Indeterminate problem. Why indeterminate problem? Because we can think of that, okay, well, to think of further, see, when the bolts are subjected to shear, it is easy to think that it is uniformly distributed. But then when it is subjected to moment, in order to calculate, how much load the bolt will carry, this is the tricky bit. And that's what we are looking at here. Now, based on this assumption, this is an important assumption here. What we have done is we have got a relationship. See, this is very important because this is the relationship we need. Otherwise, what will happen is, I'll tell you, you can write the moment equilibrium equation like that. Yeah, that's your, so you take moment of all the forces about the centroid of the group. And then what will happen? You will have P1, P2, etc. equals the bending moment. That means unless you know the relationship between P1 and P2, then you cannot solve the problem. That means it will become then a statically indeterminate problem when you are calculating how the moment will be carried by the bolts. And that's why this assumption, and which gives us a relationship between P2 and P1. So once you write the moment equilibrium equation, that means take moment of all the forces, bolt forces upon the centroid, you get this equation. This is simple. Where is this 4 coming from? 4 means depends on the number of bolts. You see, bolt A and the opposite one, we can multiply by 2. So like that, it's multiplied by 4 here. And then there are other 2. So that means we have 1, 2, 3, and 4. So there are 4 bolts which are corresponding to, which will carry P1 load, and there are other 4 bolts which will carry P2 load. That's why it is 4 times, yeah. But then, as I've said, this will be a statically indeterminate. This is a statically indeterminate problem unless you apply this assumption and then say, okay, we know how the load or how the bending moment or how the shear force due to the bending moment will be carried by those bolts. Yeah. So once you know the relationship, we have only one unknown, and then we get P1 as 79.1 kilonewton. Okay. So the bolt A carries the largest shear force. This is at the distance which we were talking about before. This is 158, which you have shown in the slide before. Square root of 150 square plus 50 square. So then what happens is we now know what is the P1, which is the bolt A, which will carry the maximum shear force. But you see, we can resolve this shear force into two components. Yeah, one is in the horizontal direction, which is 71.57 degrees. See, you can easily calculate those angles from trigonometry, not a problem. So that's your P1 sine 71.57, and this force, which is P1 times cos, right? So you can see that there is a horizontal force and there's a vertical force. Now, what is the resultant shear force on bolt A? Because it is already carrying a direct shear force, right? Which is V, 25 kilonewton, plus this component. Again, so you have to add them together. Why? Because they are acting in the same direction. So that vector, so very easy. So one could just add them and then calculate what is the vertical shear force acting on bolt A. And then you have a horizontal shear force acting on bolt A. Then you again use Pythagoras theorem to calculate what is the resultant shear force on bolt A. And this is 90.1 kilonewton. You see, there are these steps involved. That means in this case, the shear force are acting in two different directions. So we calculate what is the resultant shear force acting on bolt A. Okay. Now, using the capacity table, table 10, choose M20 bolts with the shear capacity of 92.6 kilonewton, which is greater than 90.1. That means it is safe. So M20 bolts will work here. It is safe, but then you have to then check for the plate bearing capacity and plate tear out capacity as before. In this case, 20 millimeter bolt, plate thickness, this one, 430 MPa. This is 5 BB. And then tear out capacity with A equals 50 millimeter is 150 kilonewton. That means in this case, plate tear out capacity will govern. And because this is greater than, this 90.1 kilonewton, that means it is satisfactory. Okay. All right. So worth reading section 9.3.1 because it talks about this bolt group subjected to in-plane loading and these assumptions. Okay. And then we will be looking into out-of-plane loading.